Hello, and thank you for joining our Gas Detection 101 presented by Relevant Solutions and Honeywell. You may know our company by Wilson Moore, but we have recently changed our name to reflect all of the critical service solutions that we are capable of providing. We have designed, built, and serviced fire and gas detection systems for over 50 years. Together, Relevant Solutions and Honeywell can evaluate and recommend replacements and/or upgrades for your aging fire and gas detection systems. We also specialize in rotating equipment, purification, and thermal equipment. If you would like more information about any of our business units or products, please give us a call. Michael Holmes will be presenting the presentation today. He is a product specialist for Honeywell Analytics. He currently holds a bachelor's degree in management and an associate's degree in electronics. He began his career in 1996 with Zellweger Analytics, now Honeywell Analytics, which specializes in the fire and gas detection products and systems. During his time, he held several positions ranging from field service to global technical support, inside sales, training and application support, and most recently, marketing product specialist. With over 19 years of experience in the gas detection industry, serving a multitude of industries, he says that it is a great honor to be part of a life safety company dedicated to keeping people safe. Just a few notes before we get started. If during the presentation you have any questions, please type them in the question box on your go-to sidebar. I'll read all of the questions at the end of the presentation. If you have any other issues, including not being able to see or hear the presentation, please type your issue in the chat bar or text me at 713-702-9321, and I will work quickly to troubleshoot the issue. For those of you who are unsure who your account manager is, you would like to request a quote, or you would like more general information, please send me an email and I will follow up with you as soon as possible. We will have a repeat of this session next Thursday, January 14th at 10 a.m. Central Standard Time. This session will be pre-recorded, but we will have representatives on the line to answer any questions. We are excited that you have decided to join us and hope you enjoy this Gas Detection 101 webinar. I am now going to turn it over to Michael Holmes with Honeywell. Bear with us, we're having some couple little glitches. Thank you for bearing with us. We were having a few audio issues with our presenter. He should be up and coming in just a few minutes. I apologize for this delay.
Hello.
Thank you there.
I am here.
Perfect. You can go ahead and begin whenever you're ready.
Okay, sorry folks for the technical difficulties that we just ran into unexpected-wise. I do want to thank everybody for joining today's webinar. We'll be discussing the gas detection technologies and the technology surrounding the gas detection itself, as well as some additional details in regards to that. So first and foremost, what is a gas? A gas itself, gases themselves are around us in everyday life, from everywhere from the air we breathe, with the oxygen and nitrogen contained within, to natural gases such as methane, used for heating and cooking within homes and other facilities as well. And of course, man-made gases or byproducts such as car exhausts, carbon monoxide, carbon dioxide. And of course, many, many, many more gases that come into play. Gases themselves have different density levels. And what these density levels is how the molecules migrate when they are exposed to the atmosphere. So some gases are lighter than air, so they're going to migrate up to the ceiling level. Others are equivalent to breathing air or equivalent to air density itself. So it's going to remain stagnant right about 5-6 foot level. And then heavier than air gases, which will migrate down to the floor. Okay, why is this important? It's important in the nature of when you're speccing in a gas detector itself, you need to know which way that gas is going to migrate, whether it be up toward the ceiling or down to the floor or remain at eye level. You do want to note, though, however, in some applications, you will run into different variables, such as HVAC systems or even prevailing winds, that can change the dynamics of the gas as far as its directions that it will flow. Gases themselves may or may not have a odor to it, so they could be odor or odorless. In other words, just like carbon monoxide is known as the silent killer. The reason for that, it has no odor nor color, so you do not know it is present without some sort of monitor. Gases may also have color or be colorless. A prime example of that would be opening up a bottle of ammonia within your home, and you would see a white milky vapor come off the top. And basically what that white milky vapor is the color. However, you only see it right at the entrance of the bottle because you end up with dilution after the fact. Terminology as far as gases themselves are concerned. For toxic gases, they are recorded within parts per million, parts per billion, or even parts per trillion. To explain that a little bit simpler is you could take 1 million ping pong balls, paint one red, that would be 1 part per million. So the gas detectors themselves are measuring down to that small of a molecule. One interesting fact is dogs themselves have the ability to detect down even to 1 part per billion range, hence the reason why they are used for sniffing out hazardous materials. Along with toxic gases, other terms that you will run across are TWA, which is your time-weighted average. That is your 8-hour exposure limit that you are allowed to be within a specific level of gas before it is deemed hazardous. Then you have STEL, short-term exposure limit, and that is your 15-minute window that you can be exposed to a higher level of gas prior to it becoming harmful. TLV, which is the threshold limit. These are basically a value that is put together by OSHA and other regulatory bodies in regards to the TWA. And then IDLH, immediate danger to life and health, or also known as sealing. Many gases out there are very, very hazardous in the fact that once you are exposed to even a small concentration, it is very harmful. Therefore, you must evacuate the area immediately. Combustible gases or explosive gases. The terminology that comes into play here is lower explosive limit, which is basically the range from 0 to 100% LEL, and it's basically too lean to actually ignite. Then you have upper explosive limit, which is dependent upon the gas. It's above the flammable range within the too rich level to where there's not enough oxygen to finalize the flame triangle. You will run across, for open path detection methods only, LEL per meter. And what the LEL per meter is a unit of measure that was put together for the oil and gas industry as far as how big an explosion would have to be to cause significant damage. And then volume per volume. Every gas has a volume per volume value associated with it. So for example, methane, at 100% LEL, it is 5% by volume gas. Oxygen. Oxygen itself is measured in a volume per volume. You do have a range of 0 to 100% by volume gas. While normal breathing air is 20.9% by volume, most alarm levels are set to depletion rate of a 19.5% by volume, and at 16% by volume for the non-healthy person may become very fatigued. At 6%, it is fatal for everyone, even the most healthy. Then you have an enrichment, which is above the 20.9% normal, and that is typically alarm set point at around 23.5. And by the way, these are limits initiated by OSHA. And the reason for that, with 100% by volume oxygen, it is very volatile. The smallest amount of combustible gas will cause it to ignite. So why is gas detection important? Well, there are many factors of why gas detection itself is important. First, foremost, is to protect people. Secondly, is to protect infrastructure, followed by the environment. Gas detection itself is also used for gathering evidence, as well as maintaining legal compliance. Many times, gas detection is used for process control, as well as data gathering, and ironically enough, can improve productivity. From a simple stance as the higher levels of carbon dioxide, the more people become fatigued, as well as just knowing that there is safety measures put into place allows them to have a peace of mind that everything is safe in their area. And then, of course, to confirm that it is safe to reoccupy an area. Basically, on a global dilemma, every 15 seconds, a worker dies somewhere in the world from a work-related injury or even illness. This chart here shows from a 2010 report of all the different fatalities that had occurred throughout that time period. And if you look at the slice of the pies, we're looking at exposure to the harmful substances and environment as 9%, and then fires and explosion of 4%. So when you look at a 100% scheme, 13% of that, of any workplace fatalities, is actually caused or can be prevented by using gas detection as a means to evacuate sooner. I'm not going to go through all top 10 of these, but the 10 deadliest workplace tragedies in 2010. The 10 deadliest workplace tragedies in 2010. The most notable for the United States was the Deepwater Horizon, where 11 people were killed and 17 injured based off of an explosion that occurred on an offshore oil rig. They did have gas detection in place. However, it was not enabled at the time of the tragedy. So these top 10 there, and you can actually search the internet and be able to pull any of this information up, as well as others, of what can cause that. And they range from oil and gas industry to rocket fuel manufacturing to even general facilities that have occurred. So when you're looking at gas detectors and the technologies surrounding them, you need to know where to place the detectors. Again, as mentioned before, there are characteristics that will change where you plan to actually place them. So in a general stance, you're basically going to locate them anywhere there's a pipe seal or seam, if there's gas regulators or gas cylinders around, ventilation ducts to ensure that any of the gases are not being transported from one area to another, and of course regular ambient detection, and confined space. One key note on that is no two applications are the same. So there is no common formula that you can actually implement for any application where gas detection is required. You need to look at prevailing winds, HVAC makeup, and the airflow direction that it causes, as well as human and vehicle traffic patterns, and then the characteristics, of course, of the gas itself, on whether it's lighter or heavier than air, if it's a flammable or an asphyxiant. Which brings us to the next slide, the three main categories. Flammable, of course, is any gas that is explosive or can create a fire risk. Toxic is anything that can cause poisons, such as carbon monoxide, phosgenes, and chlorines as such. And asphyxiants are those that deplete the oxygen. So oxygen deficiency, of course, as well as nitrogen and carbon dioxide. Anytime you see the NFPA symbol, which shows you the reactivity of a specific gas, not only tells you that there is a need for gas detection or potential need for gas detection, but it also tells you what that chemical compound, whether it be liquid, vapor, or solid, what kind of reactions that it will have, not only on your health, but its flammability characteristics, instability, and then any special instructions. That all leads us into the technologies themselves. So we're going to start off with electrochemical technology, where it's toxics and oxygens. Electrochemical technology, we kind of categorized up into two different categories, with non-smart sensing technologies as well as smart sensing technologies. And realistically, the only difference behind them is the raw cell used for sensing of gases. It has no memory, it has no parameters, it just gives a simple signal output. And I'll discuss that later within the next slide. So therefore, the electronics or transmitter needs to be designed to and is dedicated to the specific gas, range, alarm set points, which typically may or may not be user adjustable, as well as any other adjustments that may be required. Now, as technology advanced, we took that raw element and we added smarts to that, and basically added electronics to it. So therefore, you can have all your parameters factory defaulted by design, factory configured, and you're using just a generic transmitter or a generic set of electronics for the units themselves. And then the sensor itself dictates its gas, its range. It allows the user to be more flexible as far as alarm set point adjustments, and in even some cases may even allow you to change the gas type with no impact to the overall setup. So how the electrochemical technology works. Its basic construction is, of course, as a housing, has a sample and a reference electrode. Within that housing, it also has an electrolyte or some sort of acid base, typically a gel, and then a filter membrane. And basically what it does, and I'm going to move on to the next slide, is the filter membrane actually, excuse me, the filter membrane itself helps to eliminate potential cross interferences by not allowing larger molecules to be able to penetrate into the sensor body itself. Once the molecules actually enter the sensor, it is now exposing itself to the electrodes as well as the electrolyte. And as that happens, it is causing a chemical reaction within the cell itself, and it's actually supplying an output, whether it's in nanoamp or even microamp, so very, very small signaling. The same concept holds true for any AA, AAA, or even 9-volt battery. The only differential between an electrochemical cell and a battery is we're waiting for that one missing element, which happens to be the gas. So the animation here kind of gives the picture of the molecule coming in, exposing itself to the electrolyte and the electrodes, and giving you a current output to which the transmitter itself then can interpret how high the concentration is. Combustible bead technologies for flammable-based gases. Catalytic technology, which is another term for it, has been around since 1959 for detection of combustible gases. It is an electrocatalytic type sensor. You'll hear it known as bead technology or even polyester technology. The basic construction is a platinum wire, which is coiled similar to the old filament light bulbs, but it has a coating on it with some sort of ceramic material. Along with that coating, it also has a catalyst put on it as well, creating a bead. And if you look at the bottom right corner or even the top right corner, you will see pictures of the bead. It is very, very, very small. You do have a sample and a reference, just like any other technology that we will be talking about. And basically what it allows is the sample bead is designed to where it allows the gas molecules to permeate into the actual platinum coil through the bead and burn, while the reference bead remains constant, and therefore your center output, which is referenced as 01 here, will be the variable as far as the input or the output that comes into play, and is typically in millivolt signaling. Of course, every technology does have some pros and cons surrounding them. The catalytic technology is very, very fast in responding. It is sensitive to where it can be ranged anywhere from 0 to 20% by LEL or 0 to 100%. However, it is not fail-safe to poisonings, such as sulfurs, silicons, phosphates, and even leads, and can also be inhibited by fluorinated hydrocarbons or even chlorinated hydrocarbons, refrigerants basically, from actually detecting gas. They are very low power, anywhere from about our Honeywell analytics beads are approximately 2.9 volts to 3.5 volts operation. They are very low cost, but they do require high maintenance. The animation here shows the actual molecules, combustible molecules. If they are too large, they will not permeate into the bead itself. And as they migrate over to the platinum coil, they start creating hotspots. And those hotspots then allow that coil to expand or contract accordingly to give you a millivolt output. We get into infrared and ultraviolet technologies. And these are typically used for hydrocarbon-based gases as well as volatile organic compounds. There are three different infrared technologies that we'll be discussing. FTIR, Fourier transformer infrared spectroscopy, NDIR, non-dispersive infrared, photoacoustic NDIR, as well as ultraviolet technologies, PID. The FTIR technology is the only technology that can distinguish between gases. Every gas does have a fingerprint. And if you look at the image on the screen, it shows you the actual spectra that that particular gas will give you. So normal atmosphere, you do have CO2 as well as oxygen. But then if you look on the right-hand side, NF3, nitrogen trifluoride, was actually exposed, giving you this image. So again, it is the only technology that can distinguish between gases. This technology is typically used within laboratory environments, as well as some process environments as well, with some pretty sophisticated high-end machinery. NDIR, non-dispersive infrared. Again, you do have a sample and reference. The wavelength itself actually determines what gases that will be measured. They're typically either hydrocarbons or even refrigerants. And basically what it is the sample itself passes through into the chamber. The infrared light is then sending off to the sample in the reference detector. And as the molecules come in, the molecules actually divert or absorb the actual light source. And they're the two different filters on the sample and the reference detector will then determine how much gas concentration is available. This image here is doing the exact same thing using NDIR technology, except for it is using dual source and dual detectors. And there's a rationale behind that. The rationale behind it is there are actually 4 different methodologies for doing the exact same thing. Starting at the bottom, working our way to the top, is a single source, single detector. Then you have single source, dual detector, dual source, dual detector, but only the sample detector, the measurement detector or source, is actually going through your measurement path. And then you have dual source, dual sample, where everything is going through the measurement path. The realistic aspects behind that is the very top one is by far the best technology out there. It allows for compensation, preventing the detector to not to drift. It also gives full compensation as far as temperature and humidity and all the other factors that come into play. Photoacoustic NDIR is using a little bit different methodology. First and foremost, it cannot be distinguished between gases. No NDIR technology can. And basically what you're doing is you're sending an infrared light source through a modulated signal, so you're actually chopping the signal. And as you chop the signal, you're then sample draw the system into some sort of measurement cell, and you lock it in place. And then you bombard it with the infrared source. Using a narrowband and broadband filter, that allows you to distinguish within a range of infrared of what molecules that it will respond to. when you lock it into that single source and being bombarded with the infrared signal, it creates a pressure. It causes the molecules to become energized, start moving around, and therefore creating a pressure, and then you're measuring via pressure measurement off the system itself. Just like taking a can of soda, shaking it up, creating the pressure, and then you open it up and you release it out. You continue that process. Photoionization detector, PID, again, is typically used for VOC monitoring, volatile organic compounds, such as solvents, alcohols, alkalines, esters, ethers, and so on and so forth. But they will not react to nitrogen, carbon dioxide, oxygen, or even combustible gases such as methane and hydrogen at LEL levels. It's basically, you will see for sick building syndromes, for formaldehydes and things of that nature. Basically what it is, you have a UV lamp, an ultraviolet lamp, with positive ions moving through the cathode, and then the negative electrons toward the anode. That causes distinct change in current, and therefore giving you a measurement output. So as the lamp actually sends it off, it's charging the molecules, and it sends it one direction or the other. And based on the measurement between the two, anode and cathode, it gives you the actual corresponding reading. It is a very destructive form of detection. So it's actually literally blasting off the molecules and breaking them apart and then pulling them in to actually measure them. Paper tape technology, used for toxic gases only. And what paper tape technology is a colorimetric technology. It's commonly used, known as paper tape or chemcassette monitoring. And basically what it is a very sensitive, it is the most highly sensitive media for detecting gas. It can reach down to parts per trillion levels within specific gases, and is the only technology that actually physically gives you a physical evidence of any sort of gas release. And how the technology works, I have a little video here which will actually explain it for you. And basically, I'm not sure if the audio is coming through, so I'll explain it. As you pull your molecules through a sample draw system, the actual molecules themselves create a physical stain on the tape, as you can see in the center of the screen. From there, we actually optically measure that by sending out a light pulse and looking at the density change as it reflects back to the detector itself. So we're not looking at the physical color, we're actually looking at the density change. Of course, as mentioned before, sorry folks, didn't mean to bounce it around too quick on you. There are advantages and disadvantages for all the different technologies out there. We do have a chart that we have put at Honeywell Analytics has put together, and it is available on our website. If you search for the gas book, you're more than welcome to go to our website, honeywellanalytics.com, search for the gas book, and this chart is actually located within. So advantages and disadvantages for catalytic technology. Advantage, it's a very low cost, proven technology for flammable gases. However, disadvantages, as mentioned before, they can be poisoned, which render them inoperative, and they also do require oxygen to be able to work properly. Electrochemical, can measure toxic gases to actually relatively low concentrations, or a wide range, and they are very low power. However, the disadvantage to that is the failure modes are unrevealing because the electrochemical cell does not have any intelligence to that. It's all built around the electronics that are designed for it. And the positioning itself is very critical. Infrared or point infrared detection and even open path infrared detection, these are by far the best as far as for measuring combustible gases versus catalytic on a hydrocarbon base. There are some disadvantages. They are very high cost. There's no doubt about that. There's also anywhere medium to high power. There is a wide range of different gases that can be done as well. The semiconductor technology, which we did not talk about, this technology is very robust. It can actually work in high humidity conditions and such. However, it is very susceptible to contaminations, changes to the environment, such as temperature and humidity fluctuations, and they are not linear as far as the response are concerned. The paper tape technology, again, very, very high sensitive as far as for measuring toxic gases. It does leave evidence, so you can get physical evidence, so you really do not have any false alarms or perceived false alarms. However, they do require an extractive system, as well as so in some cases the sample lines may need to be conditioned to prevent moisture buildup within. And then FTIR technology, again, is the only technology that can distinguish between gases. However, the FTIR sensitivity is based on the cell length. The different toxic and combustible gases that cannot be detected typically are levels at the TLV and the half TLV are not exactly detectable. So at this point in time, I would like to open it up for any questions that may be. I also like to offer an invitation to joining us on either January 21st or 28th for a flame detection portion of the program. And then if your colleagues have not been able to attend today, we will be rebroadcasting this on January 14th at 10 a.m.
It doesn't look like we have any questions just yet. We'll give a few more minutes.
I do want to apologize once again, folks, for the technical delays that we had had.
Looks like we're still question-free. We have had participants start logging off, so if you guys do not have any questions, we'll go ahead and exit the meeting. If you do have any questions, please feel free to send me an email. That email address is within your registration information, and I'd be happy to reach out to Michael Holmes if there's any issues. Thank you guys for joining us, and like Mike said, we will be rebroadcasting this on January 14th at 10 a.m. Central Standard. If you have any questions in between that time, please reach out to us, and we'd be happy to help. I hope you guys enjoy the rest of your day as well as the rest of your week, and we hope to hear from you soon.
Thank you very much, folks.